This is my third video on naming ionic compounds, and I just picked out some random examples that I think would be good practice for this. So when we look at this first one, we have Mg3, PO4 in parentheses, and a 2 outside. Now we know it's an ionic compound because it begins with a metal and it has a polyatomic ion in there. When you are working with a formula for an ionic compound, I think what works well is look at the metal first. Find it on the periodic table, because that's going to tell you how much work you have to do for this. So find magnesium. It is an alkaline earth metal, so it's in the second column. It is atomic number 12. And in your reference packet, on that periodic table, it does not have any numbers in the upper right-hand corner. So it only has the possibility of having a positive 2 oxidation number. Now that means it's a little easier for us to work on this one. All we have to do is write the name of the metal and then find the anion. And in this case, it's PO4. It is a polyatomic ion. So go to your polyatomic ion page. PO4 is phosphate. So you write it just as phosphate. You don't change that ending. But pay attention to the ending, right? Because the ending depends on what type of polyatomic ion it is. And then if it's binary, which means the anion is just a single element, the ending is going to end in IDE. So for this one, it was pretty straightforward. It is just magnesium phosphate because magnesium does not have more than 1 oxidation number. But when we look at the one to the right, Fe2SO3 3, find iron on the periodic table. It's atomic number 26. In the upper right-hand corner, it has a 2, 3. That's telling you that iron can be either +2 or +3. It is multivalent. So we have to figure out which iron it is. You cannot just say iron sulfite, for example. So to do this, imagine this compound is kind of split in half. You have the cation on the left, that's the iron. You have the anion on the right. That is the negatively charged ion. We know what SO3 is. It has an overall charge of -2. You get that from your polyatomic ion sheet. Now there are 3 of those -2 charges. So that right-hand side is a total of -6. Right? Because remember, when you do this, you have 3 of these. Each one is supplying a -2. So that's why we have a -6 on the right. So that means the cation has to be +6 to balance it out. Now there's 2 irons in there, and they have to add up to +6. So that means each iron is supplying a +3. Right? You can tell that because of that subscript of 2. So that means each iron is +3. So now when we name this, we have to take that into account. So you have iron 3, and SO3 is sulfite from your polyatomic ion list. So you get iron 3 sulfite. I'm going to scroll down a little bit. If we have MnPO4 and a parenthesis 2, find manganese on the periodic table. That is atomic number 25. Now that has several different oxidation numbers or possible oxidation numbers. It could be a +7, a +6, a +4, a +2, or a +3. Now it's tempting when you look at this one that manganese, one of the options for oxidation number is a +2. So it's tempting to look at this 2 and just say, well, it has to be manganese 2 because I know I had to crisscross the oxidation numbers to get that subscript of 2. But it's not going to work out like that in this case. You can't always take that shortcut. It's not always going to work. We know what phosphate is. PO4, according to our polyatomic ion sheet, has a -3 charge. Now there's 2 of them in there, so that means the right-hand side is a total of -6. And the left-hand side has to be +6 to balance it out. There's only 1 manganese in there, so that whole left-hand side, that whole cation, that +6 charge is coming from that 1 manganese. So now we get manganese, and we have to put the Roman numeral 6 in there, and PO4 is phosphate. The reason why we end up having to do this is because we can reduce the subscripts. So for this question, if we're working backwards now, say we start off with manganese, that's +6, phosphate, that's -3. When you first crisscross those numbers, you would get Mn3 PO4 6, and that 1 and that 6 reduce to give you what our original formula was, which was Mn PO4 in parentheses and a 2 outside. So remember, always look at the metal first, see if it's multivalent, and in this case it was, right? Manganese can have a bunch of different oxidation numbers, so you have to look at the other compound in there, the anion in this case. Look at the charge for it, figure out what the charge of the cation is, and then assign a Roman numeral for that. Now Ca3N2, this one is binary. There's only 2 different types of elements in there. You have the calcium, which is the positive charge, and you have nitrogen, which is the negative charge. So when we name this, when you name binary ionic compounds, it's always going to end in IDE. So same thing as we did for the other examples. Find calcium first on the periodic table. It's an alkaline earth metal. It's atomic number 20. It is not multivalent. It only has the option of being +2. So we do not need to look at Roman numerals. We don't have to do what we did over here for manganese, where you have to figure out the charges. You just get the name of the metal. It's calcium. And since it's binary, nitrogen becomes nitride. It'll end in IDE. If you have a binary compound, it will always end in IDE. Now, you can get some that end in IDE that are not binary. If you have hydroxide, for example, or cyanide, they're polyatomic ions that end in IDE. And there's a couple of them, like bisulfide. But if it's binary, it's always IDE. Okay, I'm going to move up. All right, now if I give you the name and ask you to write the formula for it, figure out what each piece is before you move on. So aluminum, find aluminum on the periodic table. Its only option is to be +3. Now sulfide, it is ending in IDE. You are not going to find sulfide on the polyatomic ion list. This is one that is binary, so you find sulfur on the periodic table. It has a -2 charge. So what I like to do is figure out the pieces before I put them together. Now the easiest way to do this is to crisscross the oxidation numbers. So from the 2 from that sulfide, that charge, gets written as a subscript for aluminum. The 3, that is the charge on the aluminum, gets written as the subscript for sulfide. And the reason why we do this is we want the charges to cancel out. These things should be electrically neutral. So if you look at this example, Al2S3, just to double check our work, we know sulfur or sulfide is a -2 charge. There's 3 of them, so that's -6. We know aluminum's +3. There's 2 of them, so that's +6. The reason why we crisscross the oxidation numbers is to make sure these things end up electrically neutral. It's just a nice quick way of doing it. The next one over, ammonium. Ammonium is a tricky one. It's a polyatomic ion. It is the only one that we work with that has a +1 oxidation number. Now carbonate, since it ends in ATE, that is a giveaway. You have to go to the polyatomic ion sheet. It is CO3 with a -2 charge. Now when we crisscross these numbers, we're going to have to put ammonium in parentheses, because this 2 from the carbonate goes with the ammonium. So if you have to add a subscript to the to a polyatomic ion, you have to put that polyatomic ion in parentheses. Now we write down the CO3 like always. Now ammonium has an oxidation number of 1, but you don't actually have to write an oxidation number here. So I'm just going to take that out. Having a 1 written is the exact same thing as not having a 1 written, so we can leave it out. But that's how you do those. Figure out the pieces first, and then put them together. Alright, chromium 6 oxalate. Chromium is one that has several oxidation numbers, and 6 is one of them. It could be a +6, a +3, or a +2. So you can't just say chromium oxalate. It's not giving enough information. You have to say chromium 6. So we have Cr, that's a +6. Oxalate, again, it's ending in ATE. So you have to go to your polyatomic ion sheet. It is C2O4 with a -2. We crisscross the numbers. The charges, the oxidation numbers. So this 2 from the chromate, this 2 from the oxalate goes with the chromium. And now we write down the oxalate. This 6 from the chromium is going to go with the oxalate. So now what we have here is we have this 2 and this 6. We can reduce those. So you get Cr for the chromium, and you get C2O4 with a 3 outside of the parentheses. Remember, if you can reduce the subscripts, you have to. You can't leave it as this. Now, when I say if you can reduce the subscripts, remember when you are working with a polyatomic ion, so C2O4 for example, that 2 and that 4 has to be there. You can't change that part of the polyatomic ion. You can only change the subscripts that are outside of the parentheses for a polyatomic ion. So you're changing how many you have of that ion. You're not changing the chemical makeup of that ion. So magnesium chlorate, for example. Find magnesium on the periodic table. It's Mg with a +2. Chlorate is ClO3 with a -1. So we crisscross the numbers. Write down the magnesium first. The 1 from the chlorate would go with the magnesium, but you never actually have to write a 1 there. So now we can write the chlorate. The 2 from the magnesium gets written as the subscript for the chlorate. Now we can't reduce anything here, so we just leave it how it is. MgClO3 in parentheses with a 2 outside. So remember, when you are naming ionic compounds, so when you're writing the name for them, the Roman numeral refers to the oxidation number of the cation. The Roman numerals only ever go with metals, so they're only ever going to refer to positive oxidation numbers. When you're writing a formula, so like Cr, C2O4 in parentheses and a 3 outside, and the magnesium chlorate that we had, if you have more than one of a polyatomic ion, you have to use parentheses. All right, that is a general setup with these things.